In last video we saw about first derivative using first principle method and also the product rule, and today now I am going to talk about what is quotient rule, like quotient rule of differentiation. Consider there are two functions u and v, u divided by v, and I want to take the differentiation of this function as a whole. So what we do, the first thing is that you might think that if I differentiate u, then if I differentiate v, and this is equivalent to differentiation of whole, but this is wrong. So there is a rule you have to follow while doing differentiation of when two functions are divided by each other. So first numerator, numerator let it be there, denominator you take the square of the denominator function, and the start with v, let the v be denominator function. So if I multiply v, square the v and also multiply v on numerator and differentiate the numerator part, minus write the u and v dash. So this is the rule of quotient rule, and let us see with an example. For example, it is very evident that we know the differentiation of 1 by x is differentiation with respect to x. 1 by x is minus 1 by x square as a direct result. But let us see, let me take it in the form of u and v. So what is u? U is 1 here and v is x. So if I take in this form, then u is 1 and v is x. So let me take the product rule. So v square, so x square in the denominator, and then multiply with the x, and differentiation of u. What is differentiation of constant is 0. So minus write the u and differentiation of v. Differentiation of x is 1. So it's nothing but 1 into x power 1 minus 1, that is 1 into x power 0, 1. So this is very clear that this will become 0 minus 1 by x square. So minus 1 by x square. But this, in this case we don't need to use the product rule, but I am showing that the product rule you can use here also in case you don't remember the formula or forget it. Direct result. So for example, now I am going to begin with an example of a product of a quotient rule. So let me take a polynomial function first of all. So I will take an example of that. So let the f of x, let the f of x be sin x. Again I will take the tan x, so sin x by cos x. What is the differentiation of this? Compute the differentiation using product rule of tan x. So tan x I can write as sin x by cos x. And also to be very particular, we know that tan x differentiation is secant square x. Differentiation of tan x is secant square x. So I am going to compute, we already saw that using the first principle method how I am going to compute the derivative of tan x, and now using the quotient rule I am going to show you how to do. So now with this one example of tan x, let us see how everything we can remember, all the results. So sin x differentiation we know it is cos x. Let me write there, sin x differentiation is cos x. cos x differentiation is nothing but minus sin x. So now using the UV method, here u is equal to sin x and v is equal to cos x. So u by v whole prime is equal to, whole prime implies differentiation, first derivative. So first I will take v square. V square is nothing but cos square x, cos x whole square. Then I'll multiply the with v cos x into u dash. So into u dash is nothing but differentiation of sin x is cos x. So into cos x minus, it's always advisable to put the bracket. So similarly I can multiply with u, now sin x, differentiation of v, cos x differentiation is nothing but minus sin x. So this is very clear now that cos x into cos x is cos square x. So now minus minus will become plus. So plus sin square x by cos square x. So this is nothing but, we know from trigonometric identity that sin square x plus cos square x is equal to 1. This identity is valid for every angle of x, for each x. So I can write this as 1 by cos square x. Now 1 by cos square is nothing but secant square x. 1 by cos square x is nothing but secant square x. Or this I can write secant square x is nothing but secant of x whole square. Always remember that these two are similar. And don't confuse with sec of x square. This is different. This is a different thing. So this is what using quotient rule we have found the derivative of tan x. Similarly, if I want to find the derivative of what if I want to find the derivative of secant of x? Because let me show you that 1 by I can write tan x in the form of sin x into secant of x, right? Isn't it? So now if I want to compute tan x using product rule, then I should know the derivative of secant of x. So isn't it? So how I am going to know it? So let me compute the derivative of secant of x again using the product rule. So secant of x. So let me take f of x is equal to secant of x is equal to 1 by cos x. Again I am going to use the quotient rule here. Here u is equal to 1 and v is equal to cos x. V is equal to cos x. V is equal to cos x. So if I write v square, if I write v square is nothing but cos square x. So cos x into u dash is 1, differentiation of 1 is 0. So cos x into 0 minus of u into v dash. V dash is cos x differentiation is minus sin x. So we have already checked it how to do this differentiation of cos x. So now I write cos x into 0 is 0, minus into minus it will become plus sin x by cos square x. So this is interesting result because I can split this as sin x by cos x into 1 by cos x. So this can be written as tan x into secant of x. So the differentiation of tan x into differentiation of secant of x is tan x into secant of x. So now I'm going to compute the differentiation of tan x using it. So how I am going to compute the differentiation of tan x? F of x is equal to tan x is equal to, I can write sin x into secant of x. So using the product rule, now I am using product rule. Previously I used quotient rule. First I used the first principle method to compute the derivative of tan x in the previous video. So now how I am going to do that? Let me have that result here. So first I can write uv. Differentiation of uv is equal to, you can take derivative of anything, one keeping taking the derivative of one and keeping the other one same and adding the both. So this combination, this is valid for any number of terms. So now let me take the derivative of sin x. First let me take the derivative of sin x. Sin x is nothing but cos x. Sin x derivative is cos x, and v is nothing but secant of x. I will write as it is, plus again if I multiply with u into v dash. Now I will take the differentiation of sec x. This is nothing but tan x into secant of x. So now this is very clear now that if I want to take the differentiation of so cos x into sec x is 1. So this is very clear now, because 1 by sine cos x is nothing but 1 by cos x 1 by secant of x. So this will be 1, this product will be 1, and also this will be tan square of x. So because sin x into let me simplify it, this tan x is already there, and sine into secant is nothing but also tan. We know that sine into secant is already tan, so tan x from the expression. So I can write 1 plus tan x. So 1 plus tan x differentiation is secant square x. Now because why? Because using the identity, trigonometric identity, 1 plus tan square x is equal to secant square x. So this is the answer. So we have got the expression for differentiation of tan x expression using first principle method, one using first principle method, then using quotient rule, product rule. So this is very clear now that how we are going to use it. And also one more thing, if you notice that anyone would have noticed that tan square derivative, tan x derivative secant square x. And you know that this identity of 1 plus tan square x is valid only between 0 and 90 degree. If you remember from the trigonometry class, this is valid between only 0 and 90, not 0 to 90. So this differentiation, I am giving an example. This differentiation is not applicable everywhere for all values of x. One thing you have to remember. There will be a particular range for which this differentiation will be applicable. That I will talk when I talk about functions. I will talk about sets later on. Okay, so today I am going to stop with this. I'll continue in the next video how to I will start with the basics of sets and also functions, how to what are functions and how sets and functions are required to learn more about the calculus like continuity and differentiability and other things. Also, it will be useful to learn during limits. Always it is important to know when the function is valid, because function, for example, if I take f of x equal to 1, this is continuous everywhere. 1, it is a constant function. But if I take f of x is equal to 1 when x is greater than 0, when x is greater than 0, when x is greater than 0, and minus 1 when x is less than 0, this kind of function is not continuous. In this part, because at x equal to 0 the function value is undefined. By not continuous I mean that at x equal to 0 the value of function is undefined because it is varying, right? Very clear that it is not either minus 1 or plus 1, it is in between the minus 1 or plus 1. So this type of function is it is not differentiable. I mean that I cannot compute the derivative of this type of function. And this topic is beyond the scope for class 11. You will learn more in class 12 about this. So with this I will end this video.